Hello everyone, this video is about redox reactions. So in class we've talked about precipitation reactions that generally form a solid, and we've talked about acid-base reactions where you have an acid reacting with a base, and if it's a strong acid or a strong base, your products are simply salt and water. And we haven't talked about the other types of acids and bases, but that's okay. We'll get to that at a later point in time. But now I want to direct your attention to something called redox reactions, and you may have heard of these in the past, but redox is simply an abbreviation, or a portmanteau actually, and what it stands for is reduction oxidation reactions. Now, in reduction oxidation reactions, what happens is that a species is either oxidized, which means it's losing electrons, or it's reduced, which means it gains electrons. So a good way to remember that is to take a look at these acronyms. That's oil rig. That means oxidation I lose, reduction I gain. So oil rig again, oxidation I lose, reduction I gain. And that's of course losing to the electrons that are referred up here. The other one is Leo the lion goes grr. Leo stands for lose electrons during oxidation, and grr is gain. Oops, sorry, I messed that up. It should be GER, not GRR. I apologize. It's Leo the line goes grr, gain electrons in reduction. So again, oxidation, you lose electrons, reduction, you gain electrons. Simple, easy to remember, and also pretty easy to apply. So let's take a look at this. Here we have several examples of oxidation and reduction for different species. So if we have, for example, Fe2 plus going to Fe3 plus, let's take a closer look at that. And in this reaction, let's figure out what's happening to the iron. So the iron is going from a state of 2 plus to a state of 3 plus. How does it do that? Well, in order to go to a more positive state, iron has to lose an electron. So it's giving up an electron. So it's actually written, or should be written, as this. It should be written as Fe2 plus Fe3 plus an electron. When it loses or gives up that electron, it is being oxidized. So this iron is being oxidized. Okay. Let's take a look at the oxygen species. Oops, sorry. Let's take a look at the oxygen species. It's going from O2 minus to O2. Now you may be wondering, what's the charge on the O2? Well, I think if you look at your book, and you should have already looked at your book and looked at the oxidation rules, you'll notice that all atoms in their natural state, like for example, oxygen is always found as O2 in nature, they always have an oxidation charge of 0. So in fact, this oxygen has a charge of 0 on it, so we're going from a charge of 2 negative to a charge of 0, so this oxygen is actually losing 2 electrons. 2 electrons. And is also being oxidized because it's going from a charge of 2 minus to 0. Okay? So now we have fluorine. Fluorine in its natural state as F2. As I said earlier, will have a charge of 0. So that's going to get a 0. And it's going to a F minus charge, which means it's actually gaining electrons. It's becoming more negative. So it's actually gaining 2 electrons because I have 2 fluorine atoms and each one is gaining an electron, so that's 2 electrons gained in total. So this is actually being reduced. The fluorine is actually being reduced. And notice that when things are oxidized, the electrons are liberated, which means that they're written on the right side of the reaction. And when they're being reduced, they're written on the left side of the reaction. So here's another one, which is sodium. And with sodium, we start off with a natural state of 0, and it's actually losing an electron because it's becoming more positive. So that is going to be plus 1 electron, and of course it is being oxidized. So, the main takeaway here is that when species lose electrons, they're oxidized. When they gain electrons, they're reduced. And look at where the electrons are written properly. Okay. I can't stress this enough, you need to make sure that you know the oxidation state rules in your book. Like, for example, all atoms in a natural state have an oxidation state of 0. Another rule to know is that oxygen always has a state of 2 minus, unless, of course, it's O2. All group 1 metals always have a charge of +1, unless they're in their natural state. All halogens generally have a -1 charge, unless, of course, they're diatomic in their natural state, where then they would be 0. So those are just super easy rules to follow, and you will get used to them very quickly. Now, let's do some examples. Let's assign some oxidation numbers to every single atom that exists in each of these examples. So, I've already mentioned that all atoms in their natural state have an oxidation state of 0. So N2, found in nature as N2, will have an oxidation state of 0. Let's look at CO2. So in CO2, I know that the molecule is not charged. So I need to set this up algebraically. I know that the molecule in total has no overall charge on it. So what I'm going to do is I'm going to set the whole molecule equal to a charge of 0. Great. Now, I know that oxygen always carries a -2 charge with it, unless of course it's O2 by itself. So I have two oxygens, and I'm going to write that here, and they both carry a -2 charge. Now carbon can vary, right? We don't really know what carbon is. We have to determine what carbon is by using our algebra. So I have one carbon, so I'll write 1x plus my quantity 2 times -2 equals 0. So in this case, x equals +4. So that means that my oxygen will carry a charge of -2, and my carbon carries a charge of +4. Okay, let's look at HCl. H is almost always generally +1. Cl is almost always generally -1. +1 minus 1 equal to 0. It's a neutral molecule. That should make sense. If I set that up algebraically, the whole thing equals 0. I know that H is always +1. Cl is generally -1. So that makes sense. Okay, let's take a look at number 4. In number 4, we have a negative charge, and it's only one negative charge. So that means that the whole molecule is equal to -1. Now, again, oxygen is almost always -2, and I have 3 of them. So 3, -2, and I'm solving for n, which varies in state, so I'll give that an x. So x plus 6 equals -1, so in this case, x equals +5. So let me write that here, x equals +5. That means that my oxygen carries a charge of -2, and to balance everything out, my nitrogen carries a charge of +5. And finally, we have oxalate ion, C2O4. And in this case, the whole molecule is equal to -2. Oops. -2. And my oxygen, again, carries a charge of -2. And I have 4 of them. Now, in this case, I have an unknown charge on the carbon, but I don't have just one carbon. I have 2 carbons. So to make up for that, instead of just writing an x, I'm going to write 2x, because I have 2 carbons. So then I have 2x minus 8 equals -2. So when I rearrange it algebraically, I'll have 2x equals 6. So in this case, x equals +3. So that means that my oxygen is carrying a charge of -2 as always, and each carbon carries a charge of +3. Okay? So I know this was super quick, and we'll try more examples in class next time we meet.